7.2 Principle of Conservation of Linear Momentum. So from the oh my gosh, now this is getting a little bit complicated. Oh wow, okay. So I forgot to mention before in the other video that momentum has to deal with external forces, and the reason being is not nuanced at all actually, but it's quite simple logic here. Um, so let's take a system here, and I'll explain a little bit about two bodies later, or not two bodies I guess, but how linear momentum works with two moving objects. So let's say this is a hockey stadium, and there's two pucks just floating around. If the pucks collide, what happens? So let's say the pucks collide. Well, the momentum of the system doesn't change. This being because there was no work done by the surroundings. Nobody came in and pushed the puck. The pucks were just moving just over the place, and they hit each other, meaning that regardless of it, if it's elastic, meaning if all the motion is just conserved and it goes other way, regardless of that, the momentum is conserved because the velocity is the same. So I guess we would also have to redefine the thing for two objects. So so it would be m1 times v1, which remember, linear momentum is just m times v, so it's m1 v1. So let's say that this is the first particle or first puck, second puck, plus m2 v2 equals the linear momentum of p1 plus p2. Logical here, and we'll use this in other calculations. But here they're basically saying if that impulse must be an outside applied force, because if it's internal, then that means all the impulse or force cannot be added because that force was already there. That change of velocity just gets transferred into other things, and we'll explain that a little bit more. So I explain it in English because this looks kind of intimidating. Remember, PF is just linear momentum final minus initial. So it's just the same thing as impulse of PF minus PO, which is just VF minus MBO, same thing. Assume the mass stays constant. But again, we can also extrapolate this linear momentum into M1V1 plus M2V2 minus M2. Oh, sorry. Yes, minus M2. M1 plus. Sorry. I'm a little rusty. I haven't done this in a while. So, minus M1 V1. So it's the same exact term here, I guess. Oh, I guess we can factor things out, right? But no. Actually, no, you can't really. This is really the simplest one. M2 V2. I guess it'll be initial, and the masses are constant pretty much, and then F. So this would be the formula here, to calculate this. But if we're saying that there's no net external force, that means no one came in and pushed the puck, not even wind, nothing pushed the puck. Then regardless of if this slows down, and loses velocity or kinetic energy, which is again it's just 1/2 mv squared. So regardless of whether the puck slowed down, momentum is conserved, because it was because nothing changed inside the system. That's the logic there. Kind of like non-conservative forces. If there are no non-conservative forces or nothing is acting on the system, then that means MVO and MV must equal each other. Because that means that they are perfectly in sync. In other words, using this formula mathematically, we can rewrite this as 0 equals PF minus PO, and PO equals PF. So logic there, pretty simple. I guess that would be MVF equals MO. In an isolated system, no external forces, the total momentum stays the same even though individual momentum may change. So again, like in these two puck systems here, let's take this entire system, for example. And I use the pucks. I actually use an example of skaters here. If we take the ice rink, let's say that it's completely isolated. Let's say that there's, I guess, bedrock around this area. These two pucks here, regardless of if they're hitting and if one is slowing down, if the other slightly slowed down as well, that doesn't matter because there was no net external forces. It would be external impulse that leads to a change in linear momentum. But if there is none, then there is no change in linear momentum, as specified by the original formula that we mentioned in the impulse momentum theory relation. Internal forces cancel in pairs because of Newton's third laws. So again, remember, every force has an equal and opposite reaction, so that's why we don't lose momentum there. So they cannot change the total momentum. That's pretty clear. It's kind of like think of it like chemistry. I don't know if you guys have taken it. Actually, I'm trying to think of like an example here. It's really hard to explain, so I can't really. I mean, yeah, okay. In chemistry, and let's draw a beaker here. Let's say that this beaker is completely untouched. And we can think of chemistry like a bunch of tiny balls just bouncing on each other, whatever. In quantum physics, it gets a much more complicated. I mean, and in chemistry too. But in this thing, all the balls aren't moving the same speed. So we use, I guess, the Boltzmann equation. Yes, to calculate with the Boltzmann constant to calculate the temperature, because temperature is just the average of the molecular speeds in here. I think it's 3,000. Wait, no, forgot what it was. But oh no, wait, yeah, I could solve for it, but I'm not going to right now. But in this case, the molecules aren't moving at the same speed. And over time, some of the molecules will bump into each other and change speed. So let's say this one is pretty fast right here, but then it hits something and becomes slow, and the other one becomes faster. Regardless of the state of the system, no one came in and added heat to the system, agitating the system even further. In this case, it's the same thing with the pucks. Nobody came in and pushed the pucks, meaning that the momentum must stay the same, and the momentum was transferred somewhere in between here because every force vector has an equal and opposite force vector. So me pushing this puck will lead to them pushing the puck back, and that's just logic there. Momentum, same thing as before. Energy conservation depends on the type of collision because kinetic energy, because like the pucks can slow down. There can be a change in the kinetic energy. Um, um, but momentum always stays the same. If it has zero external force, not always the same. Only in the cases with zero external force. That's the logic there. I could do a few homework questions if anyone is confused. But that is the logic behind 7.2.